Hello everyone, my name is Elizaveta Kabanova and today I will present our research titled Comparison of HOG-based classical classifiers and CNN models for diabetic retinopathy diagnosis. This work was conducted by a collaborative team of Elizaveta Kabanova, Natalia Kuznetsova, Katerina Ivanko and Vishesh Kukarni for the 9th International Workshop on Computer Modeling and Intelligent Systems. So, diabetic retinopathy is a progressive retinal disease caused by chronic hyperglycemia that damages retinal blood vessels and is one of the leading causes of vision loss in adults. Accurate staging is essential for timely treatment and prevention of irreversible vision loss. While deep learning methods show strong performance, traditional machine learning approaches with handcrafted features such as histogram-oriented gradients remain efficient and interpretable alternatives. However, most existing studies focus mainly on accuracy, whereas in medical image analysis, model reliability is equally crucial, since highly confident but incorrect predictions can lead to serious clinical consequences. So this study performs a comprehensive confidence-aware comparison between HOG-based classical classifiers and a CNN architecture incorporating focal law, adaptive attention mechanism, and Monte Carlo dropout. The main contributions of this work include the development of unified framework for a fair comparison under identical preprocessing and balancing conditions. Furthermore, we extended uncertainty analysis from standard estimation to confidence correctness alignment metrics. Finally, we provided a reliability-centered interpretation of model behavior in diabetic retinopathy classification across fundamentally different paradigms. The overall workflow of the study consists of four main stages, beginning from preprocessing of fundus images to class balancing and augmentation, to model training for both deep learning and classical approaches, and finally confidence-aware evaluation. Importantly, all models were trained under identical conditions, which ensures that the comparison between classical machine learning and deep learning approaches is fair and unbiased. For the study, we used a APTOS, a 2019 blindness detection dataset, which contains slightly more than 3,000 color fundus images, manually labeled into 5 classes, indicating disease severity. So the dataset is highly imbalanced, with class 0 dominating almost half of samples, while classes 1, 3, and 4 are slightly underrepresented. Moreover, most fundus images exhibit uneven lighting, black borders, and artifacts, which can affect the pixel intensity distribution and the stability of model training. Additionally, the dataset was split into training and validation subset using 80-20 ratio to ensure reliable performance evaluation and generalization. Our preprocessing pipeline included several case stages to enhance pathological patterns in fundus images. Firstly, we removed black borders using pixel intensity thresholding and resized all images by 224 by 224 pixels. Next, we applied normalization and Gaussian blurring to reduce high-frequency noise. Finally, we combined the blurred and original images to enhance vessel structures and applied clash to improve the visibility of subtle retinal details. To address class imbalance, we performed oversampling of minority classes using data augmentation techniques such as horizontal flips, brightening adjustments, and rotations. After balancing, the training set was expanded to 9,025 images. Our proposed deep learning architecture is based on transfer learning with a dense-net 121 backbone pre-trained on ImageNet. The convolutional base was partially fine-tuned by unfreezing the last 20 layers, and Gaussian normalization was applied to stabilize feature distributions. To enhance representational capacity, we integrated adaptive convolution block attention models to focus on clinically relevant structures, which adjust both channel and spatial attention based on feature variants. To address epistemic uncertainty, Monte Carlo dropout with a rate of 0.3 was incorporated during inference. Finally, the network was optimized using focal loss to enhance sensitivity to severe stages of the disease. The model was trained using the ADAM optimizer with a batch size of 32 for 30 epochs. As a baseline, we used the histogram-oriented gradients to encode local structural information. Each image was converted to grayscale to allow the descriptor to focus on intensity-based structural information such as vessel and lesions. We evaluated several parameter configurations to determine the most suitable representation for retinal structures, and as a result, the final parameter include 9 orientation beams, a cell size of 6 by 6 pixels, and a block size of 2 by 2 cells. Feature vector were normalized to improve robustness against extreme intensity values. We evaluated two main classical classifiers, including supported vector machines and random forest. For SVM radial basis function, kernel was selected due to its effectiveness in complex and high-dimensional feature space. We also utilized a one versus one strategy for multi-class grading to achieve more balanced decision boundaries. For the random forest model, we evaluated the influence of the number of trees on stability and performance. Moreover, for both models, we applied principal component analysis with 160 components, which was determined based on the highest quadratic weighted kappa on the validation set. Performance was evaluated using quadratic weighted kappa as a main metric, as it accounts for the original nature of disease stages and the different weights of classification errors. To evaluate model reliability beyond simple accuracy, we implemented several confidence-aware measures, including area under risk coverage curve and error AURC. Finally, the confident evaluation quantifies the difference between the mean confidence and correct and incorrect predictions. It is important to note that confidence is defined differently for each model. For instance, for CNN, it was obtained via Monte Carlo dropout, while for SVM from one versus stress classifier, and for random forest as the maximum predicted probability. So the results demonstrated that the SNN model achieved the highest overall performance with a QVK of 0.92 and AUC of 0.97. It also shows the lowest AURC of 0.03, indicating superior reliability under uncertainty-based ranking. Moreover, the CNN demonstrated more consistent classification performance across all classes, including underrepresented ones, which we discussed previously. In more traditional approaches, the SVM model demonstrated the strongest performance with a QVK of 0.85, while random forest generally underperformed, but applying PCA notably improved its classification performance, increasing the QVK to approximately 0.78. These figures illustrate the confusion matrix for the SVM model and random models and their confidence distributions for both correct and incorrect predictions. So the superiority of the CNN model suggests that learned hierarchical feature representations provide a substantial advantages over handcrafted descriptors like HOG in representing complex retinal patterns. While HOG captures local gradient structures, it remains limited in handling class-specific variations and imbalance. Our SVM model showed that classical approaches remain competitive when combined with strong handcrafted engineering, showing a strong separation between correct and incorrect predictions. However, the CNN achieves the best balance between confidence level and reliability, making it better suited for clinical decision support scenarios, where identifying unreliable predictions is critical. Moreover, the random forest results remain weaker than those of SVM and ECNN, despite the increasing number of trees. It was also discovered that the introduction of PCA led to moderate improvements, suggesting that dimensional reduction helped improve noise. An important finding is also that reliability is not determined solely by the magnitude of confidence, but by how well confidence correlates with prediction correctness. In conclusion, our study confirms that confidence evaluation is essential for medical image analysis. Deep learning offers superior performance and more reliable confidence estimation, making them well suited for clinical support systems. Nevertheless, the HOG combined with SVM approaches remain a robust and computationally efficient baseline for source-limited environments. Overall, the study highlights that confidence evaluation is essential for building reliable and safe medical decision support systems. Further work will focus on and external validation or on diverse datasets and explore alternative uncertainty estimation methods. Thank you very much for your attention.